The automotive industry may have just received a major wake-up call. After months of speculation and anticipation, one of the biggest developments inside Giga Texas is finally coming into focus. Tesla Giga Press 4.0 is here. This isn't simply another manufacturing upgrade. It represents a potential 4x leap in production performance, with a mechanical system designed to challenge the traditional assembly methods that have shaped the auto industry for more than a century. So, just how extreme could Giga Press 4.0 be? The first major advantage lies in its cycle speed and structural integration. Earlier mega casting generations, ranging from 6,000 to 9,000 tons, already transformed manufacturing by combining around 70 stamped steel components into a single rear underbody casting for the Model Y while eliminating hundreds of weld points. With Giga Press 4.0, Tesla is pushing that concept even further. The system is designed to cast complex hollow box structural sections of an entire underbody in a single cycle lasting roughly 80 to 90 seconds. By combining advanced 3D printed sand core technology with AI-assisted algorithms controlling alloy flow, Tesla can optimize injection speeds and mold filling with extreme precision. The numbers are impressive. Instead of a conventional body shop relying on hundreds of welding robots and thousands of welds over extended production cycles, Giga Press 4.0 could establish a much faster production rhythm, potentially producing close to 1,000 casting modules per day. This level of consolidation could dramatically increase output per square meter of factory space and help remove one of the biggest bottlenecks in high-volume vehicle manufacturing. The second major dimension of the upgrade is its potential role as the backbone of Tesla's Unboxed manufacturing process. This approach is designed to support future mass-market vehicles and products such as the Cybercab. Traditional assembly moves a vehicle body through a fixed linear production line, requiring workers and machines to install components in increasingly restricted spaces. Tesla's Unboxed concept changes that structure by allowing different vehicle sections to be manufactured simultaneously. The large structural casting can then be combined with the battery system, seating structure, and other components through automated processes, reducing the need for traditional sequential assembly. The potential financial and operational benefits are significant. Tesla's combination of large-scale casting and the Unboxed manufacturing concept could target major reductions in direct manufacturing expenses, factory footprint, assembly time, and manual labor requirements. The critical factor that could make this approach difficult for traditional automakers to reproduce is Tesla's broader material science ecosystem. Simply purchasing a massive casting press from suppliers such as LK Machinery or IDI would not automatically allow another automaker to duplicate Tesla's manufacturing process. The machine is only one part of the equation. Material chemistry, mold design, cooling systems, software, automation, and production control all have to work together. Tesla's aluminum casting process is designed to survive extreme thermal conditions as molten metal moves through the mold and rapidly cools during extraction and solidification. To manage these demanding production speeds, advanced automated inspection systems can also be integrated into the process. AI-powered X-ray inspection and computer vision technology can examine castings for defects, dimensional issues, and geometric tolerances at high speed. If these systems achieve extremely low defect rates at production scale, Tesla could gain another major manufacturing advantage. Ultimately, Giga Press 4.0 represents more than simply a larger machine or a faster casting cycle. It reflects a different philosophy of vehicle production. By combining improvements in cycle speed, factory footprint, cost efficiency, automation, and structural integration, Tesla is attempting to create a manufacturing model that looks very different from the conventional automotive assembly line. And there is another potentially important development hiding behind Tesla's manufacturing strategy. What if Tesla could increase the output of existing GigaPress machines without constructing entirely new factories? That possibility could come from advances in specialized tooling materials and additive manufacturing. Tesla has developed technology involving 3D printable steel alloys intended specifically for demanding gigapress tooling applications. The objective is to create material that can maintain high strength at elevated temperatures while resisting the thermal fatigue that normally damages conventional casting tools. This addresses one of the biggest challenges in high-pressure die casting. Traditional tool steels often force engineers to balance hardness against toughness. Extremely hard materials can become brittle and crack after repeated heating and cooling cycles. Tougher materials can survive thermal shock better, but may gradually soften or deform when exposed to extreme temperatures. Tesla's approach suggests an attempt to achieve both characteristics. According to the patent technology, Tesla engineers used computational simulations to study carbide formation and phase transformations before developing steel compositions optimized for additive manufacturing. Rather than simply creating another high-strength steel, the broader concept combines alloy chemistry, 3D printed cooling channels, and post-processing heat treatments into one integrated tooling system. That distinction matters because one of the biggest limitations in modern gigapress operations may not be the press itself, but the ability to remove heat from the mold efficiently. Large casting tools commonly use drilled cooling channels. These work well for relatively simple geometries, but they can struggle to reach complicated areas inside massive structural molds. That can create localized hot spots, slowing solidification, increasing thermal stress, and accelerating tool wear. Tesla's proposed solution is considerably more advanced. Metal additive manufacturing can allow engineers to create conformal cooling channels that closely follow the shape of the casting surface. Instead of relying on simple straight passages, the cooling channels can curve through the tooling and maintain a more consistent distance from areas where heat accumulates. That allows heat to be removed more evenly during the casting cycle. The potential production impact is substantial. Large gigapress systems can operate with cycle times of roughly 80 to 90 seconds while generating thousands of tons of clamping force as molten aluminum is injected into the mold. At extremely high production volumes, every second becomes important. If improved thermal management eventually reduces cycle time by even 10 to 15 seconds, theoretical production capacity could rise significantly. Depending on operating conditions, that could potentially translate into dozens or even hundreds of additional castings per day from a single machine. For a company attempting to manufacture millions of vehicles annually, even a relatively small increase in production efficiency can have a major financial impact. The material properties involved are also significant. Tesla's patent describes alloy compositions containing controlled amounts of carbon and nickel along with elements such as chromium, molybdenum, vanadium, tungsten, manganese, copper, and cobalt. These combinations are intended to produce stable microstructures capable of maintaining performance under repeated thermal stress. The company has also described hardness targets exceeding 40 HRC, with certain variants reaching more than 50 HRC under specific testing conditions. Some laboratory results reportedly showed that selected alloys maintained high hardness after extended exposure to elevated temperatures. Other variants remained above certain hardness levels after prolonged high-temperature aging, outperforming several established commercial tool steels in the reported tests. This matters because a well-designed tool can combine a hardened, wear-resistant exterior with greater toughness deeper inside the material. That combination can help resist both surface degradation and crack propagation, two major causes of tooling failure in high-pressure casting environments. Perhaps the most important part of this technology is what it reveals about Tesla's wider manufacturing strategy. As Tesla moves toward increasingly large structural castings and expands its unboxed manufacturing approach, thermal management becomes more important. Larger castings contain more material, retain more heat, and are more difficult to cool evenly. Any improvement in cooling efficiency can influence production speed, dimensional accuracy, tooling life, and manufacturing costs. That's why this technology extends beyond metallurgy. Tesla is effectively redesigning the tools used to manufacture its vehicles. While competitors may focus primarily on improving the casting machine or adjusting production schedules, Tesla appears to be addressing the underlying problem by developing smarter tooling capable of handling greater thermal stress while removing heat more efficiently. If these technologies perform successfully in full-scale production, the benefits could extend far beyond longer-lasting molds. Faster cycle times, lower maintenance requirements, reduced downtime, more consistent castings, and greater factory throughput could all contribute to lower production costs across future Tesla vehicle programs. The most remarkable aspect is that the breakthrough isn't necessarily a new vehicle, battery, or robot. It is a material and tooling innovation buried deep inside the manufacturing process. Yet if Tesla can transform these laboratory developments into reliable factory technology, advanced 3D printable steel could become an important part of the next generation of gigapress manufacturing. But why could Gigapress 4.0 become such a serious challenge for traditional automakers like Ford and GM? The impact of a massive gigapress extends far beyond the physical size of the machine. It could also reshape the economics and logistics of vehicle production. Legacy automakers still depend heavily on complex assembly structures involving numerous components, suppliers, transportation routes, and manufacturing stages. Tesla's large-scale casting approach attempts to eliminate much of that complexity through extreme component consolidation. A traditional stamped steel underbody can require dozens of separate components, creating dependencies across a large supplier network. That fragmentation increases logistics requirements and exposes production systems to disruptions involving transportation, international trade, material shortages, or supplier delays. Tesla's casting strategy replaces many of those individual components with a much larger structural aluminum casting. The result is a simpler manufacturing flow with fewer major components and potentially fewer suppliers. That logistical compression can reduce internal transportation requirements and simplify factory operations. When geopolitical problems, severe weather, shipping disruptions, or missing components interrupt conventional assembly lines, a highly integrated manufacturing system could potentially be more resilient. The production economics are also important. Traditional stamping and welding processes require multiple manufacturing stages, equipment, labor, and material handling operations. Large-scale casting can consolidate many of those steps into a single process. If Tesla can reduce the amount of material handling, welding, machining, and assembly required for each vehicle, the total manufacturing cost could fall substantially. The use of modular mold inserts with advanced internal cooling channels could provide another advantage. By controlling thermal hotspots more effectively, Tesla could potentially extend tooling life while reducing maintenance and replacement costs. Longer-lasting molds would mean fewer production interruptions and less money spent replacing expensive tooling. These manufacturing improvements could ultimately support Tesla's strategy of producing lower-cost mass-market vehicles at high volume. The goal isn't simply to build a cheaper vehicle. It is to create a production system where the vehicle can be manufactured quickly enough, efficiently enough, and at sufficient scale to make lower pricing economically viable. And the potential durability benefits are another part of the equation. Large structural castings can provide highly integrated vehicle architectures with fewer joints and welds. When properly engineered and validated, reducing the number of structural connections can simplify the body structure and potentially improve consistency. The competitive advantage created by GigaPress technology, therefore, isn't limited to manufacturing speed. It can influence supply chains, factory design, tooling, labor requirements, material usage, production costs, and vehicle architecture at the same time. That is why the gap between Tesla and traditional automakers could become more difficult to close. Legacy manufacturers would not simply need to purchase a massive casting machine. They would need to redesign factories, supplier relationships, tooling systems, materials, software, quality control processes, and vehicle architectures around an entirely different manufacturing philosophy. That could require years of development and enormous capital investment. Meanwhile, Tesla can continue refining the system through real-world production. This is what makes Giga Press 4.0 so important. It isn't merely about increasing the size of a casting press. It is about compressing dozens of manufacturing steps into fewer operations while connecting advanced materials, automation, software, tooling, and vehicle design into one integrated production ecosystem. If Tesla succeeds in scaling this approach, the biggest advantage may not be the machine itself. The real advantage could be the entire manufacturing system built around it. And that could force traditional automakers to rethink how vehicles are designed, how factories are organized, and how supply chains are structured. Tesla's manufacturing battle is therefore not simply about building cars faster. It is about changing the economics of producing them. And if GigaPress 4.0 delivers even a portion of the efficiency improvements Tesla is targeting, the consequences could extend across the entire automotive industry. Thanks for watching. Make sure to hit the like button, subscribe to the channel, and turn on notifications so you don't miss our next breakdown. See you in the next video.